of engineers in any society, that you must recognize that your position is to solve engineering or the challenges that the society has. And one of the major societies that we have across Africa, and actually the whole world, is access to clean water and, of course, entirely sanitation. Some interesting statistics says that by 2050, over 70% of the population in the entire world will be living in urban areas. In Africa, most of our cities and urban centers are developing rapidly. There's a lot of urbanization. Infrastructure are very outdated. Others are very overwhelmed. I mean, even from our local estate here, when it rains, it pours, and there is effluent, the system is completely overwhelmed. Many people have come into the urban areas. Who is going to save the situation? It's you, engineers. And most importantly, you are young. You're going to be here, God willing, because I believe God is going to give us a good life. We're going to be here for like 30, 50, 60 years from today. So the knowledge you're acquiring today is not about getting a certificate. It's not about getting a job. Of course, I know the job will keep you moving. We also need to look in the long term. After all of this, where can I be able to apply this knowledge? So Nancy, Sia, Danielle, Sifuna, and everyone else, I don't want you to have a tunnel vision about your next job. You're now an engineer, now you're in structures, you're in this. The universe is going to be opening a lot of opportunities for you today, tomorrow, or in the days to come. You must be prepared for that. Now, to look at the implications and the impact of sanitation to our lives, I would like to play a short video. And after this short video, of course, I'm going to be expecting some feedback from you. And we said that learning, and when you come to these webinars, is you get information through your ears, you synthesize, apply it contextually, to where you are, the challenges that you have, and then you give us feedback. You give it out. It's like how bees do it. They take nectar, synthesize it, and then give us honey. When you teach yourself every educative webinar that you go into, approaching it in that perspective, then the learning sticks. So ladies and gentlemen, welcome one more time to this interesting and super educative webinar that we're going to be having on sanitation of waterborne, systems. And I'm going to be sharing a video with you so that you can learn and share feedback with us right now. So please confirm whether you can be able to see my screen. Please confirm. Just drop a 1 in the chat box if you can be able to. Looks like my screen is jangled up. Let me just share one more time. One more time. Just give me grace. Great. Fantastic. There you go. Great. So please confirm you can see
You've probably used water today already.
And probably you can see the audio. Just drop a 1 in the chat box. That will be sufficient.
Apart from cooking or mopping the floors, think about how you use water to care for your personal body. I'd like to share with you how. Think back on the ways you've probably used water today already. Apart from cooking or mopping the floors, think about how you used water to care for your personal body. I'd like to share with you how I used water already. I got a drink of water when I first got up this morning. I used water to cleanse my toothbrush, to brush my teeth, and to rinse out my mouth. I used lots of water to shower with and to wash my hair. Then I used water in the sink to shave my face and a little bit to smooth back my hair. When I went to the toilet, it was water that carried away the waste down a tube somewhere far out of sight and out of mind. And then, after the toilet, I washed my hands with soap in the sink. Water is necessary in each of these instances to either replenish my body with fluids, to wash away the wastes from my body, or to keep my body free from germs. These three categories of health, sanitation, and hygiene. Water is also used for cosmetic purposes when I shave or wet my hair to keep it in place. In fact, regarding health, men need to consume about 3.7 liters a day, or about a gallon of water, and women need to consume about 3/4 of a gallon. About 70 to 75% of our human body weight is water. The blood is 82% water, human brain is 85% water, and it is no wonder that some of the early symptoms of dehydration are fuzzy short-term memory, trouble with basic math, or difficulty in focusing on small print, because your eyes use a lot of fluids to do their work. What does water do in and for the body, we should ask? Well, it serves as lubricant. It forms the base for a saliva. It forms fluids that surrounds the joints. It regulates the body temperature, for example, through perspiration. It helps to alleviate constipation by moving food through the intestinal tract and eliminating waste products. So it's a very fine detox agent. And finally, it regulates metabolism. That is how our body gets energy from its food. So our thirst is a natural signal to our body that it needs water. And when people don't drink the only other water they can get, dirty water. Water is used to do two things regarding sanitation: to dilute the waste and to move it to a place where it can be treated. For many centuries, before there were very many people on the planet, human and animal bodily waste could be released into a river or stream. When the waste is sufficiently small, water has enough volume to dilute the waste and render it harmless to people who might be living downstream. The world and the amount of water it contains has and will forever be the same. It will not increase. But as populations have increased, it has become much more difficult to find enough water to dilute waste sufficiently. This is especially true in the industrial or developed world, with people moving into larger and larger cities, as you heard during the last lecture about London, Chicago, and Milwaukee. Well, this brings us to the second usage of water in sanitation: to carry it away to a place for it to be treated or disposed of. A very old system still in use today is called the septic tank and system. The water carries the waste by gravity from the home to an enclosed tank. There the solids will settle to the bottom, and the liquid water flows out the top of the tank into a drain field where it percolates into the soil. There, natural bacteria in the waste and in the soil have time to degrade the waste and make it more inert or safe. Septic systems can be very effective ways of using water to transport wastes, but only in places where population densities are small and there is plenty of land for the water to be spread out. A more modern system, and one that's used in large developed cities, is one in which water is used to carry the waste to a centrally located waste treatment plant, or called a wastewater treatment plant. And there, in the treatment plant, natural processes are mimicked using engineered systems, in effect doing the same thing that the bacteria would do in nature, in that soil that we spoke about, but in a more controlled and speedier fashion. Then, once treated, that water can be re-released into a river or a lake or a stream, where it will not have an adverse effect on either ecology of the water body or people living downstream of it. The third important category is hygiene. It refers to those practices that we do to maintain and preserve our health. Specifically, hygiene in the home and everyday life settings plays an important part in preventing the spread of infectious diseases. Now, many of these practices require water. Hand washing, as we've mentioned, hand washing in the sink, proper rinsing of food, care and cleaning of domestic animals, and other practices that are generally considered proper hygiene, including bathing regularly, washing scalp hair, keeping hair short, wearing clean clothing, and brushing one's teeth. Some practices are even gender specific, such as those used by a woman during her menstrual cycle. Hand washing is probably the most important single behavior that can be implemented in a developing country to reduce the risk of infectious diseases. Recall how every hospital has numerous hand washing stations throughout the patient care floors, and visitors are required to wash their hands before entering a patient's room. Let's take a look at what is often called the F diagram. The F diagram shows various pathways that pathogenic or disease-causing bacteria can take from feces to future victim, that is, you or me. The fecal material, if it is not deposited in an isolated place, such as a latrine or a toilet, can easily find its way into water, into fields where crops are grown, or fingers of children who are playing. Finally, flies often carry bacteria from the feces to your food, which is why we often cover our food. Some of these pathways lead directly to your mouth, as when you drink contaminated water or touch your dirty fingers to your mouth. Or they lead to your food, which of course leads to your mouth. Once in your mouth, you are at increased risk for the diseases that these pathogenic bacteria will carry. It has been estimated that almost 1/10 of the global disease burden, the total global disease burden, could be prevented by improving water supply, sanitation, hygiene, and management of water resources. That's all diseases. Childhood underweight causes about 35% of all deaths of children under the age of 5. An estimated 50% of this underweight or malnutrition is associated with repeated diarrhea or intestinal nematode infections as a result of unsafe water. Such underweight in children is directly responsible for about 70,000 deaths per year. But we'll talk more about these diseases in the next lecture.
All right. Thank you very much. I know most of you are wondering, what does this have to do with engineering? And that's the question that I would like you to answer for us. What is the space of engineers in sanitation? And what are your takeaways from the video? Please, the session is open. Anyone, anywhere has an opportunity to share with us. Please, let's go. Please unmute and share with us what is the space of engineers in the whole sanitation side. Yes, Sifun, do you want to speak?
Okay, I may want to share some information concerning water as engineers.
Yes,
Most likely,
please.
you find out that we, the engineers, we are supposed to design the sanitation systems that will treat the wastewater management. Especially like now, you see, water is what we use for life. And after using water, we get that most of the 3/4 of the water that we use go to waste. And like you are using in a house, you are flushing toilets, you are washing hands, you washing utensils. All that water that has used now become it can be a waste and supposed to be trained away from the house. So you as an engineer, you need to look for the way you are going to design the systems that will treat this water so that it can be used or reused or it can be disposed in a well to improve the hygiene of the place you stay. I think that's what I can share.
Thank you very much, engineer. You have shared the context of our household. Thank you very much. One more person, please. Justin, Leslie, how are you, gentlemen?
Hi, good. Well, thanks.
Great. Anyone else who would like to share, please? We want to jog our thought.
Just a minute, I'm parking. Hold on, hold on.
Thank you, Justin. Your network is a little bit unstable. You can drop in the chat box. Okay, one more person. What is your space in the sanitation cycle as a civil engineer, whatever kind of engineer you are? What is your space in that entire cycle? And how can you make it better to enhance public safety or public health and safety? One more person. Fantastic. So thank you very much. Just for us not to spend a lot of time, it looks like we really don't know the space of engineers in the sanitation cycle. It means that probably if we were to step out to get a wash interview, for example, you are applying as a wash practitioner, you are also probably getting a job in an industry that entails sanitation and water systems. I don't know what your answer could be, but of course, that should not be a problem for any of you. And that's why you're coming into this very lecture and this online webinar. This webinar is organized to help you answer specifically that question that I have talked about. In this webinar, we're going to be talking about the conventional gravity sewers. Of course, these are the most common ones. We're going to be talking about vacuum systems. We're going to be talking about small borehole sewer systems. Of course, these are small and localized. And then also in low resource or rapidly urbanizing areas. Our speaker for today is Engineer Baron Siren from South Africa. He is a specialist in sanitation and, of course, highway design. He has extensive experience when it comes to design of sewer systems, design of sanitation systems, design of pumps, and of course, highways. He is part of our own sub team, and I would like to introduce him so that he can be able to take over from this point. Engineer Baron, please, if you're ready, your people are ready for you. Are you ready?
Yes. Thank you so much, engineer. Am I audible?
Yes, you're audible, please.
Okay, thank you so much, engineer. Yeah, thank you so much for the opportunity. Good evening, everyone. Speaking to you is Baron Sirend from South Africa. I'm probably going to just turn on my mic so that you can see me. I think that's code for. I hope you can see me. Yeah. So I'll just, yes, thank you so much. Yeah, that's me right there that you're looking at. So yes, thank you so much, engineer, for introducing me. So today I will be taking you through the webinar on sanitation. So I hope you guys, you have your notebooks with you as well. And I also hope that you will be taking down some questions because probably maybe at the end. Please ensure that your mics are muted. Please ensure that your mics are muted. Thank you so much. Yes. So also ensure that you take down some questions. Probably we're going to have a short question and answer session at the end of this webinar. So like Engineer James had already said, I'm part of the WhatsApp team. If you have been following us for some time, you realize that as an organization, we are pushing towards equipping engineers across Africa. And one of the things that we are doing is to also equip engineers in the wash sector. And I've got a couple of statistics that I have for you that I just want to share with you so that you guys can have perspective on why this is important. Just like what we always do in Rota, we always ask ourselves, why do we do what we do? Why should you guys learn sanitation? Why bother being in this space? Is the skill that you're learning even more important? I mean, one of the things that Engineer James always says is that a degree is not that important, but skills are important and should be able to solve problems in the society with the skills that you have. So you're asking yourself, what skills do I have to solve the sanitation problem in my society? Or maybe do you even know that we have a problem with sanitation to begin with? So those are some of the questions that we're going to be talking about, some of the stuff that we're going to be tackling. So I do have a couple of statistics. I was just doing some research. I've been doing a lot of research. I do work with a lot of municipalities, some of them that are in the peripherals or in the urban areas, in the peri-urban areas, some in the rural urban areas. So I do have some sort of like experience and I've seen firsthand that, especially when it comes to engineering, one thing that I really like about engineering, be it roads, what we do here, be it in structures, we're also doing that. You'd realize that there is no one size fit all, right? You're going to go on site, or you're going to almost every engineering project that you're going to do is going to be slightly different than the previous one. The concept is still the same. So with that being said, there is no one size fit all. So one of the things that we're also going to be talking about is for you to understand, to say if you're dealing with sanitation, there's no one size fit all answer. You're just not going to learn about conventional gravity sewers. And then you think in your head, okay, I'm covered. When it comes to sanitation, I'm now a guru or a master. That's not how it works. So this webinar also, that's one of the things that we are also trying to achieve here so that we can equip you so that you can have extensive knowledge at your disposal to know, okay, if I'm dealing with sanitation or if ever I'm put in this situation, what other options do I have to deal with wastewater, so to speak? So yeah, so I would say just grab your notebook, just make sure that you have your notebook. I will just switch off my camera for now. I'll tell you later when we start on our question and answer. So just ensure that you're taking down some questions and please ensure that your mics are muted. And if you do have a burning question, you can also maybe throw it into the chat box. So I will be checking the chat box from time to time. Okay. So if you've got a burning question and you really want to ask something and something that I say, you're not understanding it, please resist the urge to interject. It would disrupt the flow of the presenter. So you can just throw your question in the chat box. And then I promise I'll be looking at the chat box from time to time so that I can see and answer questions that you may have. All right, so allow me to share my screen. You can drop a 1 if you can see my screen. You can drop a 1 in the chat box if you can see my screen. Thank you, thank you. I'm seeing those ones, 100%. Thank you so much. Thank you so much. Thank you so much. Yeah. So if you can see my screen, you can see that there is Waterborne Sanitation there. And you can see that main organ that is written sewer. Okay, thank you so much, Collins. I see someone putting a tick on my screen. Thank you so much. You can erase it as well. Thank you. Right. I think that was a very good introduction from Engineer James when he was trying to engage you and ask you guys questions about sanitation. What is sanitation and why is it important? You know, why should we bother? Why should we think about this? I like the statement that he uttered that, I always have this argument with some of my friends that are doctors. They think that their profession is more important than us. And of course, being an egotistic person I am and being an engineer, I also think my profession is important. Then I then say to them, listen, if you make a mistake, one person die. I mean, God forbid, all life is important, right? I'm not saying life is not important, but if you as an engineer makes a mistake, particularly in the area of sanitation, more lives are at risk. So you'd realize that you compromise the health of generations, not only your generations, but generations to come. So let's say you're designing a sanitation system for an urban area, and then you design or you make a shoddy job, right? um, just give it a few years, your system will fail. And whenever we design systems, whenever we design infrastructure, one thing that you also need to know as an engineer that you're designing for something that is going to outlive your existence, right? Probably you're designing for 2 or 3 generations after you. So you also need to have a foresight of the impact that whatever project that you're working on has. So particularly on sanitation, it's something that we struggle with in Africa. It's also something that we struggle with, particularly in my country where I come from South Africa. There was a recent cholera outbreak sometime last year that claimed at least 120 people. That is not something that we would like to read in the news, right? And it was precisely because of sanitation issues, right? These are problems that we can deal with. And I know you're an engineer and you're thinking cholera, but yes, there is a direct correlation there because the infrastructure that we should design that should deal with wastewater, be it treating the effluent or collecting the effluent to the treatment plant, is our responsibility. So today we're just probably going to be talking about the infrastructure that carries the wastewater to the treatment plant. Probably in the future, we're also going to talk about the wastewater treatment itself. But for today, we're just dealing about how do we convey the wastewater safely from the places where it's produced to the places where it can be treated. So back to the question, sanitation. Now, I did a couple of research before I just get on the definitions that are on the screen. I found out that over 3.5 billion people globally lack safely managed sanitation, according to the World Health Organization as of 2024. Now, speaking to sub-Saharan Africa, I come from sub-Saharan Africa, and I believe we do have people from all over Africa and all over the world. Just in sub-Saharan Africa, only 28% of the population uses safely managed sanitation services. That's ridiculously low. So just think about that in perspective, that only 28%, sorry, 28% of the entire population in the sub-Saharan district of Africa has got access to proper sanitation services. Now, according to UN, they say approximately 800 children under 5 die every year from a disease that is related to diarrhea caused by safe water, sanitation, or hygiene. So we're talking about 800 children under 5. They die every day, not every year, not every month, every day. So every day, like today, approximately about 800 kids lost their lives that are under the age of 5. This is all coming back to sanitation, right? So you might be thinking, okay, how am I involved as an engineer? There is a serious crisis when it comes to sanitation. You're going to see as I make the presentation why I'm talking about these things. And they usually just show up in areas where you don't realize it. So you're going to just get these concepts, just get these pointers that I'm getting, and I'm just trying to give you perspective on how serious this issue of sanitation is. Please ensure that you mute your mics. Someone is unmuted. Thank you. Mr. Peter, please mute your mic. Thank you so much. Now, sanitation as an infrastructure, it's the core of public health. It's not just engineering, but it is the core of public health, right? So with that in mind, you have to understand that there is a need in the society. There is a need for us to understand what sanitation is all about and our role that we play as engineers to maintain and ensure that sanitation is kept at peak, right? So back to the definition that you guys are seeing on the screen. Sanitation refers to the practices involved in maintaining and improving public health by managing waste, ensuring clean water, and preventing the spread of disease. This is public health engineering. And as a wash engineer, like Engineer James, as a wash engineer, this is your responsibility. You are thinking about this. And one of the things that I was just thinking about is we rely so much on Westerners to come and solve our problems in Africa, but we as African and as engineers, we need to step up and solve our problems. This is happening in our backyards, right? This is happening in our backyard. This is happening in our communities, be it in the rural areas, be it in the urban areas that we're living. This is happening in our communities, right? So water and sanitation are interdependent and interrelated in terms of sanitation provision in South Africa. Particularly when I made this presentation, I was using South Africa as an example because this is where I live and this is where I see most of these issues happening. And I believe, as I was doing a couple of my researches as well, in Zimbabwe, they're going through some same things, Namibia, Botswana. I was actually, as an example that I'm going to show or share with you guys, recently, I believe it was sometime last year in Nairobi, there were recent floods as well. There were extreme floods, right? And that on its own as well, it also affects sanitation. And if your infrastructure is not designed properly to cater for that, there is going to be an issue as well, right? So these are all issues that are affecting us. So a sanitation service needs to offer a complete, holistic, and developmental approach to the community, which includes health and hygiene improvements, environmental health consideration, and infrastructure development. Now, note the word holistic. It has to be a holistic solution, right? Because whenever we're talking about sanitation, yes, we are going to be focusing on managing wastewater in this particular webinar and in the courses that we're going to be rolling out. But you also need to understand how it's interlinked with other issues such as your hygiene and public health engineering, right? So sanitation is very, very important, right? It's very, very important, and it's your job as an engineer to know what it means and what is at stake when you're getting yourself into this or when you're trying to solve the problem. You need to have perspective, right? So that's sanitation. Now, the stuff that we're going to be covering in this module, right, is we're going to be talking about conventional gravity sewers in the context of sanitation, vacuum sewers, small bore sewers, and then simplified sewers, right? As you noticed when you guys were watching that video that was playing at first, the gentleman was talking about a lot of things like septic tanks, availability of water and all those things. We're going to be covering all those things as well in passing as we move, but mainly we're going to be focusing about this. And one thing that I've noticed with a lot of engineers out there is that most of them or most people are familiar with conventional gravity sewers. But when it comes to vacuum sewers or vacuum system sewers, people have no idea what that is or when to use that. Or when we start talking about small bore sewers or simplified sewers, right? Like one thing that I also wanted to, one thing that I want you guys to understand is that there is no one size fit all when it comes to sanitation engineering or when it comes to engineering in general. You need to have a number of options in your arsenal. So not all the time you're going to employ a conventional gravity sewer. Not all the time you're going to have a small bore sewer system or a simplified sewer system, right? Very, very soon we're also going to be talking about the employment of your sump and your pump station as well in the sector of sanitary sewer. It's also a big, big thing. How do you design a sump? How do you size your pumps, your rising mains, and all that stuff? It's also still part of sanitation. So it's quite big. But for now, we're going to be talking about this. Okay, so this is what we're going to be drilling deep in this webinar, right? So before I go any further, I just want to probably maybe classify sanitation systems. There are basically two types of sanitation systems, the ones that use water, as you can see, it's water aided, and the ones that do not use water, right? Now, I'm going to explain exactly what happens and why you need to know these two, right? So for the ones where we say no water aided, we do not need water, right? We have got the conveyance of excreta to the wastewater treatment works. Usually the ones where water is not needed, there is what we call an on-site sanitation system, right? Now, if you've grown up in the rural areas or if you have families in the rural areas, predominantly maybe most of us are Africans, you probably have a rural area where you come from, right? Where your people come from. And in those places, it's less developed, right? And there is no access to water, right? Like usually there is like a one bowl that services the entire community. So water is not readily available. That's what we mean. Like there is water in the community, but what we are saying is we do not have water that is readily available in your house where you can open a tap and there's water that's coming out. So in that type of setting, we use what we call on-site sanitation systems, right? So that's your pit latrines, right? I'm sure you guys are aware of these ones, your pit latrines. I grew up knowing them as blade toilets. I'm sure maybe they are blade toilets as well. I'm not so sure if you guys are familiar with the term. So we have got pit latrines, ventilated, improved pit latrine. There's a lot of technology that's going into that, right? But the most important thing that you guys need to understand is that these are on site, like it's happening on site there. We do not have water. So because we do not have water, it's happening on site. Now, the reason why I'm emphasizing on this is because you need to understand that whenever you're designing, or let's say you need to solve an issue of sanitation problems in an urban area, and there is no water in the area, or there's no water that is readily accessible, you can't be proposing a conventional gravity system. That will not work because we do not have water for us to transport the waste, right? So if there is no water, then you need to start thinking out of the box. Okay, fine. What do we have? There is no water and we have space. Okay, what we can do is let's propose an on-site sanitation system. So we are going with pit latrines. So these ones, in as much as we are advancing and technology is moving forward, there are areas or certain scenarios where they are the most applicable solution, right? Like I just gave you right now, if you go in your deep rural areas where there's no access to water and there's no access to any urbanization that's happening that side, we can actually employ this type of sanitation, right? This is where you can go with your ventilated, improved pit latrines, right? This is quite simple. Then we've got the one where we've got water in the system, right? So this is typically urban areas, and I believe almost everyone that is in this webinar, you are living in an urban area. Probably, chances are high that most of you are here that living in an urban area. So chances are high that you've got water. You go at your tap, you can open and there's water. You take a shower, there's water, right? So in a system where there is water that is available, right, we can then try and employ what we call an off-site sanitation system, right? So we've got group 3, as you can see here. We've got conveyance tanks, shallow sewers, conventional waterborne storage systems, vacuum sewers. This is a scenario where we are then using that water that we have that is abundantly available to us. We use it to transport our waste. As you saw that introduction video saying, okay, listen, the water that we use, I took a shower, I cleaned my body, right? I produce waste. Then the water is then used to transport the waste from where it's produced to where it can be treated, which is probably your BNR or your stabilization ponds or yeah, whatever treatment plant that you're going to be using, but it's an off-site treatment. So the water is not being treated or the waste is not being treated where it's produced, right? So these are two distinct, like these are very important determining factors as to what type of sanitation are you going to use. So you just don't show up in urban areas and you say, okay, let's just go with a pit latrine in urban areas. That will not work, right? For a number of reasons. Number one, there is water, so there's no need for us to have a pit latrine. Number two, there is no space in urban areas. It's usually densely populated. So imagine if everybody is going to build a pit latrine in their house or in their yard, right? Right. Now that pit latrine is probably going to be full. It's not going to be full probably 10 to 15 years. So what happens when that full? You have to close that, then you have to find another place within the yard, and then dig up again. So it actually does not work. There's a town probably in Zimbabwe called Suncoast. I've been there. they employed this system called an ecosan. You guys can look it up. So the entire neighborhood has got ecosans, right? So I was very curious, and I was walking through that area, and I realized, okay, this was a very, very bad idea. Because what would happen is that it's actually becoming a densely populated area, and every house has got, for the sake of you guys understanding, let's just say every house has got a pit latrine in an urban area. Just try and picture that, right? So what then happens is that, imagine how much wastewater is pouring into the ground. It will cause a lot of problems. Probably one of them is groundwater contamination. We actually calculated and realized that we estimated about 1.2 megaliters of wastewater was being released into the ground. So imagine the amount of groundwater contamination that is happening just in that area. Then guess what's going to happen? Someone down that village or someone in that area is probably going to what? Drill a borehole, right? Then they drill a borehole. Then they what? They tap water from that aquifer. But that aquifer has already been contaminated by what? By wastewater that is being put into the ground. So this is what people sometimes do not understand when we say sanitation and water is very much linked. So particularly in that particular area, everyone now has to be prohibited to drill a borehole, because chances are high that the water that is seeping into the ground will probably contaminate the aquifers in the area. It's not all the case, but chances are high that might happen. Maybe your borehole or maybe your aquifer, you're probably going to be extracting water at 80, 100 meters deep. We do not know, but there is a possibility that might happen. So it's something like that that you have to think about, right? So that's very important. So those are two factors that you need to think about. We have got water, and we've got a situation where we don't have water, right? So you need to take those two instances into account. Now, let's start with conventional sewers, right? Conventional sewers. Now, these ones are quite easy, and they're quite straightforward, right? So a conventional gravity sewer system requires a water supply, right? Let me just quickly grab my pen. I need to be writing something here. Okay. Let's take note. Water supply, right? So a conventional gravity sewer system requires a water supply, a sewer reticulation system, a bulk line sewer lines, and a wastewater treatment works, right? So these are three things that are needed in your conventional sewer system. So we need a water supply connection. That's the first thing that we need, right? We need to have an abundance of water. If we do not have a water supply, then we're not even thinking about a conventional sewer system. As engineers, we need to start being creative and thinking about something. So if ever you've got your water supply, right, you know that, okay, fine, there's a chance that I can start thinking about a conventional sewer system. So a conventional sewer system, then it would then need you to design a sewer reticulation system. So a sewer reticulation system is just a network of underground pipes that carry that sewage from where it's produced to the treatment plant. So it's a network of underground interconnected pipes, right? So it usually starts with your house connections, then you go to your lateral sewers, then from your lateral sewers, you go to your main sewers, from your main sewers, you go to your sub-main sewers, from your sub-main sewers, then you go to your gravity sewers, then you go to your trunk sewers until you reach your treatment works, right? So that's your conventional sewer. So a main gravity sewer distribution network in a developed area conveys accumulated sewer via house connections, like I said, right? That is sewage to the sewage treatment. So the connection pipe diameter usually varies from 100 to 150. Now, I don't want to go into the details, but I want you guys to probably understand the most important things in this gravity sewer system, right? So think about this. You have water. Particularly think about this from this perspective. Whenever there's a land development project that's happening, right, you know, okay, fine, what is the type of development that needs to happen in this particular area? Okay, we see from the town planners, you get your information. It's usually a subdivision permit, you get that. Okay, you see, this is what your client is looking for, right? Okay, these are the types of houses that I want to put in this area. Then, is there going to be a water connection or a water source? Yes, there's going to be a water source. So there's going to be a water reticulation system. Therefore, you're probably compelled to use a conventional sewer system, right? You have water, so you have to design your conventional sewer system. So like I said, you need a water reticulation. Now, let's just talk about the sewer reticulation, what that means. The sewer reticulation, like I'd already said, is interconnected pipes. They are underground. Now, most of you guys live in the urban areas, and I know unless there is a problem, you hardly see sewer flowing on the roads or anywhere on your ditches, right? You hardly sewer in a functioning sewer system and in a functioning society, you must not see sewage flowing anyway. You must not even have any contact with it. You must not even know what's happening. Only the engineers should know in a properly functioning system, right? It's because sewer is, it's odious, right? It's not something that's pleasant. That's why these pipes are underground. And one thing that you also need to know, they are not just laid haphazardly. There is, I would say there is a science to the madness. I would like to say that statement, right? There is a science behind it on how they are designed. So the moment we know that we have water, we now need to figure out a sewer reticulation system. Now we know that we are thinking of pipes. Now, think about this. For conventional, it uses gravity. Gravity is your friend in this particular system, right? Your sewer has to be carried down from the way it's produced all the way to the treatment plant, all by gravity, right? There are some instances where you cannot employ gravity, like let's say the draining area is opposite to where the wastewater treatment plant is. So you might need to have a pump station and a sump to collect the sewer, then pump it to the to your waste treatment plant. That's like another different topic there. But conventionally, this is the easiest way. So the moment you have water, you're now thinking, I'm just using a conventional sewer system. So this is the most commonly used sewer system. I'm sure most of you guys know this. If you have been a wash engineer before, or if you've ever worked in any design capacity where you're doing land development projects, probably you have come across your conventional sewers. So this is how it looks like, right? So as you can see here, right, you're having houses, right? These are houses, probably this is a middle income to low income housing, right? And then they're divided. As you can see, these are just stand boundaries. So these are houses. So these dotted lines that you're seeing, they're representing, this is your sewer line. So this sewer line is underground, right? This is just a plan view that you get to see. So this sewer is flowing underground, right? And these ones are just house connections. So as you can see, all these houses, as you can see now, they're just probably going to be connecting to that sewer. So we're having one pipeline that is flowing in that direction. Then we're having these house connections, right? And usually, I'm sure you guys have seen a house plan before and you've seen the detailing of plumbing. They're usually, these house connection lines, they're usually laid at a slope of 1:60. Then the sewer line on its own, there is no set slope that you can use. Now, this is where you get into the details of the design to see, okay, which one is the acceptable slope? And depending on the manuals that you are using, because you have to also adhere to the manuals in your country. However, the science behind the water mechanics still remain the same. So this is a typical, a conventional sewer system. So the dotted lines, like I said, they represent your typical sewer lines that are underground. So these ones will be your house connections. This one will be what we call your lateral sewers. This one will probably be your main sewers. The moment we connect two or more lateral sewers, we get what we call a main sewer line. Then after we get a main sewer line, we go to the sub-main, then we go to the trunk main, and so on and so forth. So one thing that you also have to know whenever you're dealing with your conventional sewers is that your pipes or your pipe diameter increases as you go downstream, right? So you might start lateral sewers. According, I've read a couple of manuals. Most of them, they just prefer your lateral sewers to be 150 millimeter diameter. However, I like to use 160 millimeter diameter. It's a very small difference because of the availability of the material in the market. So in some places they do have 150. So don't be surprised. Someone will say 150, probably going up to 200, right? So that could be your lateral sewer. Then from 200, your 225, then you've got your 250 going to 300, 315, and so on and so forth. So also the type and the size or the pipe diameter that you're going to use, you just don't pick a pipe diameter for the sake of picking a pipe diameter. You also have to calculate you have to do what we call a capacity test of your sewer as well to see that does the pipe diameter you're picking have the capacity to carry the sewer that you want to carry, right? So too big of a diameter, a pipe diameter will cause some sedimentation in your pipe because it simply means that your pipe won't reach cleansing velocities quicker or at all, right? So you need to strike a balance between the size or the capacity of your pipe diameter and the slope as well. I'm going to talk about it as we go into the next slide. So that's your typical gravity sewer line. Now, what are the components of your gravity sewer line, right? Or your conventional sewer line, pardon? What are the components of your conventional sewer line? The components is a pedestal with a flush mechanism, right? As you can see there, then you've got your on-site sewer connection. So what you guys were looking at this side, right? This house, this is the detail, right? This is the detail, right? So you've got your on-site sewer connection, then you've got your internal reticulation. So this is the municipal reticulation. This is where you actually get to design as the design engineer. So it's something that's there's like a science to it, right? So like I said, you've got your flush system. As you can see, that's your toilet there. This is particularly your water closet. So this is only showing water from the water closet, which is your gray water, right? This is your black water, sorry. There is also the gray water, the water that you produce when probably, let's say, you do your laundry or you wash your dishes or you clean your house. You usually chuck all that water into the drainage, right? Most people, they throw it maybe into the garden to water their garden, but in most cases, you throw that water into the drainage, right? So it will probably be connected by a pipe, right, at a certain slope, right? That will then connect to the lateral sewer. So this is the sewer that we're probably going to be dealing with. So all the urban areas, they probably have this type of connection. This is the sectional view of how it looks like underground. This is how it will be looking like. So as you can see, you've got your clean outs, they clean out number one, clean out number two. These are not necessary as well. You probably need one. You don't maybe need two, but we can go into the details of that when we're now designing the conventional sewers. But this is generally the components of your conventional sewer. So let's just quickly go through it. What are the main design guidelines, right? What are the main design guidelines? So these are the three key takeaways that I want you guys to think about whenever you're looking at your conventional sewers. The first thing is your cleansing velocity, right? Your cleansing velocity. There is a minimum and a maximum velocity with typical values ranging from 0.7 meters per second to 2.5 meters per second. Now, let me explain the concept of cleansing velocity. Remember, these pipes are laid underground. So once we lay them, no, probably we won't be having daily access to these pipes, right? So we have to design these pipes in such a way that they've got the ability to clean itself. What does that mean? It simply means that there is going to be a situation where, a moment where there is going to be sedimentation built up in the pipes, right? So we need to ensure that water is going to be moving at a certain slope so that there is no sedimentation built up. You understand? So in the event that your system cannot reach cleansing velocity, which means sediments will build up. I'll give you an example. Like we are all in Africa. I've been, particularly where I lived, I actually grew up in a low-cost housing. So what would happen, or one thing that I've seen, particularly with mothers, is when they are scrubbing their pores, they tend to use sand or special type of sand, right? They would say if you're scrubbing pots, you need to use like an abrasive material. So you have to go outside and get sand. Then you scrub your pores. Then you are washing down the sink. Then you just wash all that sand into the drain. Now, that sand does not dissolve. It's not like salt or sugar or anything, right? It will probably collect into your sewers. Now, if your sewer system does not have the ability to push that sand downstream to the treatment plant, it will build up and build up and build up in your pipe, which usually causes the clogging of your pipe. So your pipes will clog, then you see sewage coming out of the manholes. We're going to talk about that as well. Right. I was actually this afternoon, I was going to the shops and I saw a best manhole in my area close to where I stay. And I actually started asking myself questions, what could have caused this? Right. So this is also one of those reasons where we are saying your sewer does not have the capacity to clean. It has to clean itself. So in some manuals, it's written self-cleansing velocity. Right. So it depends from manual to manual. Like if you read Egyptian manuals, usually they prefer, I believe from 0.6, I've read some of them, it's acceptable in their area, 0.6 meters per second to 0.665 meters per second. In South Africa, we use from 0.7 meters per second. If you do read some manuals like Van Veen, they talk about 0.75 meters per second. So this is the minimum velocity that is required to be in your pipes. So you need to know when you're then calculating your pipes to say, okay, fine, what is the projected velocity that is going to be in this pipe so that it does not clog? And also we need to have a maximum velocity of 2.5. So now this also applies when probably we're dealing with force mains, when you're now pumping your sewer, to say your sewer also doesn't need to be moving too fast, because it may move too fast and leave the sediments behind and they still build up in the system. So the cleansing velocity is very important. So these are your main design guidelines. Then from your cleansing velocity, you need to do your capacity check. So some design guidelines indicate that some sewers should be designed to flow during peak flows, although making an allowance of 15% of infiltration of stormwater. So local municipality guidelines do sometimes design for a maximum flow depth of between 70% to 80% of the pipe diameter to have surplus capacity for stormwater. So what we are saying here, let me maybe just draw something, right? We are saying you are having your pipe like that. Forgive me, it's not very smooth, right? So we're saying you're going to see, we're also going to be covering this in depth, what we're going to do for the capacity test using the Manning's equation, right? We actually do have a spreadsheet that you can use. You just plug in your parameters, then it shows you what is the capacity of your sewers, right? Is it flowing at 70%? Is it flowing at 60%? So according to most of the manuals, this will be your sewer, that the one that I'm shading here, and this will be the air. So you need to have at least your sewer flowing at a maximum of 70 to 80% and leave at least 30% of air in your sewer, right? Because most people, this is what I've noticed, most engineers probably in my country and in sub-Saharan Africa, they use the Manning's equation. So the Manning's equation always assume your sewer is flowing as an open channel. It's an open channel flow. That's the fluid dynamics that is assumed when using the Manning's equation. We're going to discuss that as well. We're also going to use the cope required, right? But now the main importance of the capacity test is you're going to calculate, because whenever you're sizing your sewer pipe, you need to understand how much sewer are you going to be getting from your community, right? So let me give you an example, right? Let's say we want to design a sewer pipe for my house, and on average, how much water do you think an average person uses a day? Let me just see. You can just drop your answer in the chat box. I want to show you guys something. How much water do you think an average person uses a day? I can see a good number of questions there. Philip is saying 100 liters. Okay, that's good. Gilbert, 20 liters. Yo, man. That is very, very interesting. You're a person that I need. You save water. Someone is saying 30 liters. Kuma. Ruramai is saying from 100 to 200. Okay, fine. Let's use 75. All right, 7 liter in an emergency, 15 liters in normal circumstances. That is very funny. Let's go with 100 liters. Right. Okay, let's go with 100 liters. So let's say you're going to use 100 liters of water a day, right? Okay, someone is drawing on my screen, right? Let's say you're going to use 100 liters of water a day, right? Now, 100 liters of water is going to come into my house, right? I'm going to shower, do everything with 100 liters. What percentage of that water is going to be generated to sewage? So this is what we call a return flow, right? So when you're doing your sewer, your capacity check, there's something that we call a return flow. So there's a return flow factor. Now it depends from manuals to manuals. Some manuals, they would say use 0.75 to 0.85 return flow factor. So in this particular example, let's use a return flow of 0.85. So return flow just simply means what percentage of water that is going to come into my house that I'm going to use, what percentage of that water that is going to go out as sewage. So we're going to say a return flow of 85%. So 85 liters of water that I'm going to what? Get into my house is going to go back into the system as sewage. So if I get 100 liters of fresh water, I'm going to release or produce 85 liters of sewage. So that's your return flow. So what then you do is that with that return flow, you have to factor out your peak flows, right? Now, one thing that you also guys need to understand is that whenever you're sizing or you're doing a capacity test, right? Like you see from this point that I wrote here, from this point that I highlighted here, we are saying that design guidelines indicate that sewers should be designed to flow at what? During peak flows. Because we always design for peak flows, right? Peak flows, this is maybe usually during the morning and evening when people are going to work, people are going to school. So almost everyone is using water at that time. So there are peak flows. So we also consider or factor in our peak factors. Then after we consider our peak factors, on that return flow, we also factor in 15% of infiltration due to stormwater. Now, no matter how perfect the construction of your sewer system is, there is going to be some water that is going to infiltrate into your sewer system, no matter which material you use, probably through the openings such as your manholes. So you need to factor all these things into your system. This is where I was having a conversation with some engineers from Namibia and all these other guys. Some other guys, they use what we call combined sewers. Some use separate sewers, right? This is also something that there's a lot of study that goes into when you want to design a combined sewer. It has got its own advantages and disadvantages. But one of the main thing that you need to know without a shadow of doubt is your capacity. Does your sewer have the capacity to carry that? Does your pipe have the capacity to carry the sewer? So if you undersize your pipes, right, your system will be overloaded, and some of the sewage will start coming out of the manholes, right? So you have to do your capacity check, right? So like I'm saying, I will probably come to the chat box and answer a few questions. I saw a question that is probably related to this, saying, what equation do you then use? I use the Manning's equation, but my favorite equation is the Colebrook-White equation. I'll also probably going to be explaining deeper as to why I prefer the Colebrook over the Manning's equation. I use both of them, and they both give good results. I just prefer the Colebrook-White equation. I've got my own reasons, but this is very important. You have to do the capacity test. You have to do it, and you have to know how and why to do it, right? Then the last one is you have to do your slope. Now, in general, sewers could follow the slope of the ground, except if there is a horizontal and adverse terrain. Now, one thing that you have to know about slope, when I always tell or teach people about the conventional sewers, I always say follow the gravity. The rule of sewer design is follow gravity or follow the slope. Never fight the slope, right? Never fight the slope. I actually borrowed this term from the traders. If you've been a trader at one point in your life, I'm sure you know that if the Fed chair Jerome Powell is making a statement, there is 9 p.m. So the markets are usually very erratic. So never fight the Fed. So when it comes to SWOT design, is never fight the slope. Always it should be at the back of your mind. Never fight the slope. In fact, one of the things that we do when, for those that will sign up for the course, we know one of the things that we do when we start to design our sewers is to figure out or do a slope analysis. We need to figure out where is the slope going. Before we even start doing cleansing velocity or capacity check, we need to figure out the slope. How is our ground? So you need to first of all understand your terrain. How is it behaving? Then you start thinking about solutions. Okay, where is going to be my drainage point? Where am I going to be collecting the sewer? And where am I going to be, if need be, to be pumping the sewer? Or with, because as you know, as much as you design your sewer systems, pumping should be the last resort that you should have, because pumping is expensive. The operation, the O&M costs are exponentially high. So we're trying to run away from pumping as much as possible. So it's always follow the slope, because if you're following the slope, you're following the gravity, and there's no gravity bill that you pay a month, and it's natural, right? So we're trying to be very cost effective. So there is a minimum slope that is required, right? So one thing that you're also going to notice is that you're going to check as well. There is a direct correlation between the slope, right? It's probably the slope is it's somehow directly proportional to the cleansing velocity, as you're going to see in the Colbrooke equation. So to say your slope does affect your cleansing velocity, right? So one of the ways that you're going to be dealing with your cleansing velocity, whether you're increasing it or you're reducing it, is by managing the slope. And bearing in mind that as well, if you have steeper slope, which means you're going to have steeper trenches, which means that your project is going to be expensive. You're also trying to run away from that. So in as much as you're going with the slope, which is very important, the more you go with the slope, the more you cut on cost of trenching, right? As you're going to see, we're going to be talking about drop manholes as well. You're going to be using some technologies as much as possible. So one thing that you need to know, that the slope is very important. So depending on the manuals that you use, I always like to use the conservative of 1:D, right? Though in our country, the minimum slopes are a bit more relaxed. So let's say if you're having a 115 or 160 millimeter pipe, they say your minimum slope should be 1:200, which is very generous, right? However, I don't like to go 1:200. I like to always use my minimum slope as 1:D, which is 1 in diameter, right? 1:D. For me, I like to always do my minimum slope as 1:D. It's a bit stricter than some of the manuals that I've read, but it also keeps me on the safe side. And usually, most of my sewers, they reach cleansing velocities quite quicker, and the velocity increases as I go down the stream. So 1:D usually works for me, and it's very, very efficient and safe. So if you're having a 200 millimeter pipe diameter, you know that your minimum velocity should be 1:200. If you're having your 160 millimeter pipe diameter, you know that your pipe should be 1:160. Your slope, I mean, your minimum slope, right? And as well, just on that note, we use AutoCAD Civil 3D. I'm sure you guys know that Rosalp is an Autodesk certified training center. So we mostly use BIM tools. So now one of the advantages of using Civil 3D is that it automatically calculates your slope for you, right? So as you change, it automatically adjusts your slope and it updates. The tools in Civil 3D, they're very dynamic and very interesting. I was also reviewing some of the drawings. I want to mention the municipality as well, but I was reviewing some of their sewer designs that were done like a long time ago. They were using 2D drafting to come up with the long sections. It was very, very tedious for them. I can imagine what they were going through. But these days we have Civil 3D, so you can literally streamline this process and you can be quite efficient in your design. So yeah, those are the main 3 points that I want you guys to take home. You need to figure out your cleansing velocities. You need to have your minimum cleansing velocities. Then the capacity, you need to figure out like 70 to 80%, right? Usually for my capacity check, I genuinely use, there is a template, a spreadsheet that I use for Colebrook, and also a spreadsheet that I use for my mannings. I just use those two to compare my capacity. Then the last one is your slope, right? So those are the three main design guidelines that you need for your conventional sewers, right? So the reason why I'm spending more time on this one is because it's the most commonly used. probably that most of you guys are going to be interacting with. Now, the components of your conventional sewer, you've got what we call your manholes, right? As you can see, these ones, you've got your manholes, and then you've got your pipes. So I'm going to start with the pipes. As you know that we've got a number of pipes that we use that are at our disposal. We've got PVC pipes, we've got asbestos pipes, we've got concrete pipes, steel pipes, cast iron pipes, glazed earthenware pipes. Now, particularly from where I come from, mostly we are now using PVC pipes. They are mostly popular now, and glass reinforced concrete as well. It's becoming a lot more popular as well, particularly if you're now doing your force mains and your trunk sewers, right? Asbestos, it's been a while. These ones are very old pipes that we used back in the day. I'm not so sure if they're being used currently in the system. Then you've got concrete pipes, yes, usually for your trunk lines. Concrete pipes are usually used, but like I said, I've seen a lot more people move into GRP, right? Then steel pipes, there are certain situations where you can use steel pipes as well, right? So one thing that you also need to know that wastewater is not only sewage, right? So maybe you might be designing a sewer system for, let's say, an industrial area that is producing toxic material. So maybe PVC would do, or maybe steel pipes would do, or maybe cast iron. It depends with the type of project that you're working on. So these are some of the pipes that you need. Then from there, we have got what we call manholes. I'm sure you guys have seen this before. I'm sure when you're walking down the road, you've seen this. Maybe some of you have never seen all this, but you've seen this. So this is what it looks like. Then this is a manhole, right? Coming from the fact that a man hole, like a man should be able to fit inside this hole, right? So a manhole, it's an opening constructed in a sewer so that the sewer can be accessed for inspection, right? So like I'm saying, one of the reasons why it's called a manhole is that a person should be able to fit in there and go down and access the pipe. So usually the pipe here, let's say there's a clogging that's happening, or they just want to inspect the flow, somebody should go in there, and if there's a clogging, they can just insert the rodding still there, then they can just unclog the pipe. So that's how it looks like. So as you can see, you've got the cover wings. So these are step iron rings, right? You can just, yeah, sort of like a ladder, but it's step iron that are probably on the manhole. Then you can go there, then you can see that there is an inlet pipe. This is the cross section. So this is what we call the channel case. Right? So this is a typical cross section of a manhole. So this is what it would look like in real life. I've actually been in one of them. Yeah, it's not very pleasant down there. Really, I respect people who do a lot of our maintenance in our cities. Yeah. So this is what it looks like. So for a conventional sewer system, you know that you have in your pipes that carry the sewer, then you're having your manhole. So manholes that can also be constructed from bricks or precast concrete rings, right? It's also called the working chambers. So they range from 900 millimeters to 1,350 millimeters in diameter. So as you know that the manhole diameter for trunk lines is probably quite larger compared to the manhole diameter of regular sewers, right? Now, let's just quickly go through the pros and cons. Now, this is probably my favorite part. Now, let's just start with the pros. A high level of user convenience is obtained, right? This is also one of the advantages. It's very, very, very convenient, right? You can just, like literally most of us, all we do is we take a shower, and after we leave the shower, we don't even care where the water that we showered is going. We don't care. When you flush your toilet, we are done. You do what you do. It's very convenient. When you wash your dishes, you are done, right? There is no, okay, I need to fetch water, I need to do this. It's very convenient, right? That's why it's mostly preferred in the urban areas. It's very, very good. If well constructed and maintained, it has little impact on groundwater quality. Like I'm saying, so your water is probably going to be flowing in conduits underground, right? So there is little to no groundwater infiltration right there, right? That is if it's well maintained, right? So no system is 100%, as you know. but this also ensures that your groundwater cannot be contaminated. So it can maintain a minimum velocity, right? Because you're using closed pipes, right? You can be able to tweak your slope so that you can maintain a minimum velocity that can ensure self-cleansing. So it's also very suited for high density areas, right? Although formal structure and layout is also equally relied. Easy access to the system, right? So these are some of the pros. I'm not going to go through them because of time, right? But one of the cons that I just want to touch on, as you can see, there are quite many, but I just want to touch on a few, is the most expensive sanitation option in terms of both capital and operation cost. Now, this is a very valid point to look at, right? It's very important. The cost is very high, right? So should we choose to go with the conventional sewer system, you need to know that your design has to be, number one, efficient, and it has to be very accurate. Any mistake that you make, it can be very costly as well. These are billions of rands, right? We're actually part of this other project, and we're comparing the cost of building a water reticulation and a sewer reticulation. The cost of building a sewer reticulation was 3 times that of building a water reticulation of the same area, of the same size, right? So let's say you are servicing 200 stands. The water reticulation was 10 rand, and the sewer reticulation was costing us 30 rand. So it's very, 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 very expensive, right? So one of the reasons why it's also expensive is because of the excavation that happens. And also one of the things that can balloon your cost in terms of your sewer is your slope requirements. It's because the minimum slopes that are required to ensure that your system can function at self-cleansing capacity. So because of that, you might realize that in some instances, you might have steep velocities. I remember I was in this town. I was just talking to the engineers, and they said, listen, do you know that in this town we've got a center manhole that is 6.3 meters deep? Now, 6.3 is not a joke, right? There is a lot of shoring that goes into that. We now need to probably inquire with your geotech engineers just to ensure for safety. So because of all those things that are concerned, your project just becomes excessively expensive. So that is one of the main cons that is associated with using conventional sewer. So I'm not going to go through them, right? Also, it requires professional expertise in terms of maintaining it and designing it. So it's not something that can be done by anyone else. It's something that can be done by engineers. So it's also something that we're going to touch on, probably building a BOQ and just seeing, okay, fine. One thing that we usually did with some of my guys was 2 people can design the same project and they cost it, and we see who has the cheapest project or who has the most affordable project. Then we go through their project and we start analyzing their project. Okay, fine. What are the decisions they've made? Why is it their project is cheaper than everyone else? Then we go for that one. So it's also one of those things that you need to understand as an engineer. We practice the skill of what we call value engineering, right? We know that projects cost money. So you also have this thing in your mind to say, in as much as there's safety, there's quality and functionality and efficiency, there's also an element of cost. There's no need for you, it becomes almost pointless for you to design a project that is going to cost us $2 billion to implement. It becomes impractical, right? So your project also has to be very, very practical in terms of implementation and so. So those are some of the pointers on conventional sewers. So before I go to vacuum sewers, let me just quickly check my chat box and see if there's a few burning questions. Someone is unmuted. Please mute your mic. Please mute your mic. I do see someone who did ask me about how do you prevent clogging in your pipes, right? It's also stuff that we then go in deep probably in the course. We're talking about the application of your grease traps and all those things, right? It's very important for you to know all that. So let me just see if I can just I've Justin, okay, you was just responding that in Barbados we call them latrines, pit toilets. All right, all right, all right. Yes, yes, I see that. Samuel is saying, what formula for pipe sizing do you use during design? Colebrook, Mannings, or any other? I use both, but I prefer Colebrook. Now, the reason why I prefer Colebrook, I'll just tell you now, is that Colebrook white is less sensitive to input parameters compared to the Mannings equation, right? So for instance, if you change the roughness coefficient factor in the Mannings equation by a factor of 2 or 3%, there is like somebody's unmuted. Please mute your mic. Now, so back to the Manning's equation. If you change just the roughness factor, there is a huge change. Like I'm not so sure about the figures as of yet. I don't remember them from the top of my head. But I remember when we changed the roughness factor from 0.11 to 0.15 in the Manning's coefficient, there was like a 6 times change in the velocity outcome, right? But in the Colebrook wide, we just changed the K value, right, which is the coefficient. I believe it was changed by 10 times, and the velocity only jumped by 27%. So the Colebrook white is more stable when it comes to input parameters. Plus the Manning's equation, it
Okay,
requires some
naweza
sort
kupata
of.
watu wengi. Jibu hapo ni yes or no. Hakuna explanation.
Simon, please mute your mic. Thank you. So yeah, I would say let's go with the Colebrook white, right? Someone is saying, under what conditions and what stage would you consider open channels for conventional sewers? Now that depends. That depends. I would say I don't really consider open channel sewers, right? That's why I always prefer to go with the Colebrook White equation, right? Because I don't like the implication of designing my sewers with the open channel implication to it, right? So I would always just go with the code required, because I'll be trying to run away from the open channel conditions and their implications in my sewer design. But that's a very good question. But I'm really willing. Maybe you can hit me up so that we can probably discuss it in detail, so that I can probably share both equations and just quickly show you what exactly I mean. All right. Let's see. Samuel is saying, can the manhole serve as means of reducing slope when you are allowed to do haunching? Can you share the Excel sheet for Colebrook White? Now, those are like two questions, so let me answer the first one. Can the manhole serve as means of reducing slope? Yes, when you apply drop manholes. So for instance, a drop manhole is a scenario where, let's see. Okay. Let me use this one. So let's say you are having two pipes that are flowing at that, right? Then I'm having another pipe that's coming from this side. That's coming from that side. That is probably connecting here, right? Then I'm having this pipe. Let's just change here. So this is my natural ground, right? I'm having pipe that's coming from that side, right? Then I'm having a pipe that's coming here. It's probably connecting from a pipe that's coming there. So this one is coming maybe at a depth of 2 meters. This one is coming at a depth of 0.5 meters from the relative ground level, right? So which means we might be forced to make everything, or I might be forced to have this pipe also come at 2 meters, right? But I can employ what we call a drop manhole. So a drop manhole usually connects two pipes that have got two different invert levels, right? So let's say the invert level of the incoming pipe is shallower than the invert level of the outgoing pipe. So I might use a drop manhole in that situation, so that I can lessen the excavation that I might need to have on the incoming pipe. Because in the old days, they used to just mesh the incoming pipe and the outgoing pipe. They just mesh them all together. So then that increases the amount of earthworks in your project, which just makes or it balloons the cost of the project. So yes, you can use what we call drop manholes. They have a number of advantages to them. Also just preventing the splashing of water or waste water in the manhole. So I would say the use of drop manholes in that particular scenario it will be a very good idea. So let me just check one more question and let's move. Sharing the code required is only exclusive to people that sign up for the course. We always give you the template for the code required in the money's equation, right? All right. Let me just take one more question so that we can quickly move through. Some highlight on connecting the main sewer to prevent its bad water in entering my system. Some more highlight on connecting the main sewer. Okay, I'll answer that. About the slope of water, is it a must to follow? Is it a must it to follow from highly area to low area? I'm not so sure what you mean, Collins, by that, but probably slope, yes, it has to flow from high areas to the low areas, right? Like we're saying, slope, always follow the slope because you're trying to take advantage and leverage your gravity in that situation. So yes, it flows from the high places to the low places, obviously, slope. Maybe you can rephrase your question. I don't really understand. What happens when the soft cleansing velocity is exceeded, and how can you make sure that it's kept within the system? That's good. So usually the soft cleansing velocity is exceeded when your slope is steep, right? So what happens? There are certain scenarios that let me maybe explain you from this perspective. There are certain instances where your soft cleansing velocity is exceeded, and one of the causes, the main causes, if it's just a gravity system, is because your slope is steep. Remember, your slope directly affects your cleansing velocity, right? So if you've got a steep slope, you know that your fee is going to be exceedingly high. Now, if your cleansing velocity is exceedingly high, it causes the scouring of the pipes. I don't know if you guys have ever noticed, but we had water problems in my area, so we're using a tank. So when I was opening the tank, the water was coming out at a faster speed. So I was very curious. I'm very curious. I'm like, okay, I need to measure the velocity of this water because it was moving very fast. And I only found out that it was moving at 0.9 meters per second. But in my head, I thought maybe it was moving at a very, very, very fast. So if ever you have got your design and you see that your velocity is exceeding 2 meters per second, it's moving extremely fast. That's very fast. So if water is moving usually at that speed, right, it has got scouring effects to the infrastructure, right, that it is contained in. So it can damage the pipes, it can damage the manholes, right? It can damage. So one of the ways that you can do is just play around with the slope, just play around with the slope. Try to have flatter slopes so that you can reduce your cleansing velocities. Now, in the instances that you cannot reduce your cleansing velocities, you might need to employ what you call energy dissipation chambers, right? Because you need to find a way to dissipate the energy of your system, right? So usually when you're connecting your pipes, we always say, let me try and explain it from this point. Whenever you're connecting your pipes, apologies for that. Whenever you're connecting your pipes, right? Let's say you're connecting them at a flatter grade. We usually say the pipe that you're connecting and you're having a manhole here, you need to maybe have a vertical drop of at least 0.50 millimeters so that you can maintain the energy grade line of your sewer system going downstream. But in the case that you have got a high cleansing velocity, you need to dissipate the energy. What do you do? Number one, use the energy dissipation chamber. So you need a manhole that will dissipate energy. So if I'm having steeper slope, right, and my sewer is coming in a manhole, right, use an energy dissipator rather than using a conventional manhole. So an energy dissipator would reduce the flow velocity of that sewer. Then by the time it leaves the pipe on the other side, it's starting the cycle again. Because if you just connect your pipe, let's say it's a steep pipe there, maybe of 1:8, then you've got another 1:6 going downwards, as you are going to see that your velocity increases exponentially as you go downstream. So if you don't have a mechanism of reducing it intermediately, it will reach excessively high levels and then it can cause scouring to your system. So one of the ways is use energy dissipators and always use anchor blocks as well, just to anchor your systems. Because if it's at a higher velocity like that, your sewer will fail. It will fail, right? So yes, that's a very good question. Let me just take one more question, then we just quickly follow through with that. Then I would like to know different types of manholes and where they can be used. Yeah, I've already spoke of, we have your regular manhole, we have got your drop manhole. I already spoke about it when you're connecting two pipes of inlet levels. You've got your energy dissipators, then you've got your your energy dissipators, then then you've got a manhole that then connects a force main to a gravity main as well. It can also act as an energy dissipator as well. So we'll also get into detail with that one. So I'll just give you three for now, but that should be sufficient. Let me take this last question. About the 15% allowance for infiltration of stormwater. Don't you think this is so conservative in design when considering closed system? If I am designing what's happening there, if I am designing a more economical system, don't you think this will become an issue which will keep my design at a higher cost? Okay. I'm trying to understand your question. About the 15% allowance for infiltration of stormwater, don't you think this is so conservative in design when considering closed system? Okay. Now, the 15%, you have to understand that when we talk about the 15%, we are also talking about, you have to take into account where are you coming from? What type of climate are you in, right? Now, for my friends in Kenya, probably 15% won't work because it rains a lot. So there's probably going to be a lot of infiltration that's happening in that area, right? Now, I come probably from a semi-arid, not arid, semi-arid place, right? So if I then increase my infiltration, because I used to use 5.25 as my infiltration for my peak wet weather flow. And when I used to do that, I used to oversize and I used to over design my systems, right? And they used to be inefficient when they are implemented. So I'd realized that 15% is a very good happy medium, but also you don't need to be very blind when you're doing it, right? Like I'm saying, it's 15% probably in my system where I am, depending on the climate that I have and on the amount of rainfall that we expect. But in different areas where we say maybe there's a lot of rainfall that might happen, chances are high that there's a lot of infiltration that might be happening in the system. So you might need to increase or have a bigger allowance of the infiltration. So I think that's a very good question, right? So yeah, it just don't have blinders. 15% is not like a one size fit all, right? Like I said, in some instances, some people use combined sewer systems, right? It's also getting to see, okay, what type of area are we designing the system in? What climate are we? Are we in a wet weather climate? Are we like in arid climate and all that stuff? So it all plays a role in that, right? Now, could you mention a sample of manuals you use? I mostly use South African manuals, Namibian manuals. I do dabble in Kenyan manuals here and there. I've used Egyptian manuals as well, some Zimbabwean manuals. So I just read around a lot, depending on which project or where I'm working. So let's say, just an example, if probably we get a project in Kenya or in Tanzania, we just have to go through their manuals and find out what's happening. So don't really be held too much on the manuals, right? Probably if you're going to be learning, even if you're going to be part of this webinar, the course, you're going to be taught according to the South African manuals, but that does not mean that it's very different from Kenyan manuals, for instance, because sewer in South Africa is sewer in Kenya. It's the same fluid mechanics is still the same. The basic concept is still the same. It might change here and there, but the change is not very much, right? So like I gave you an example. In Egypt, I believe their self-cleansing velocity is 0.6, and they are quite relaxed on their minimum slopes. So it's not that much of a big deal. But as long as you understand the concept behind it, how to design it, how to get or to make the decisions that you're making when you're doing your design, that's what's important, right? Like, for instance, I learned how to design a road using Kenyan manuals, right? And I'm quite comfortable even in my own country using Kenyan manuals. And I built on that, right? When I started using my own South African manuals, Sandra and all these other manuals to then build on that. But it's still the same, the concept of design is still the same, right? I took a lot of time with that one, so I'm probably going to try and run through. Then we have got vacuum sewers, right? I don't know if any of you guys have heard about vacuum sewers, but I was actually reading a very interesting project where they actually employ vacuum sewers, right? Right. Let me just quickly run through this. So vacuum sewers use what we call a differential air pressure to move the wastewater. So a central vacuum pump station is required to maintain a vacuum, which is a negative pressure on the collection system, right? So as you can see, you are having a house connection here, then your sewer goes into sort of like an pit sump. You've got a sump that is already in your house, right? Now that sump will be connected to a what? To a vacuum pump, right? So because of the negative pressure that is created by the what? By the vacuum pump, your sewer will probably move into the what? Into the collection tank. Now, this as you can see, there's a lot of moving parts there, right? And you can also see that it's capital intensive, right? Because we have got vacuum pumps and each house has to be equipped with a sump that will temporarily collect the water and all these other things. So one of the things that you also need to know that not it's not a very common application for a source system, right? But one thing that you also need to understand is where it's mostly applicable, because remember, for conventional sewers, we said always follow the slopes. So what happens when you go to a place where it's relatively flat? What do? Or the place is very rocky, right? Or the soil is unstable, right? Let's say you want to do a sewer system in the desert. The soil is unstable, right? Or it's a rocky or a flat terrain, like in the Cape Flats. It's very, very, very flat, right? Or in an area where there's high water table. So these are the conditions for vacuum sewers that you need to know, right? But the ones that are most obvious, like I said, flat terrain, unstable soil, high water table, right? Those are some of the things that you need to know. So vacuum sewers, I'm sure you guys have heard about this site in Palm Jumeirah in Dubai, right? I was actually watching the documentary, when was it, sometime last week, on how they built this. This is an artificial island, just so you guys know. So because it's an artificial island, they had to import, I think about 4 million metric tons of stone. They had to remove some sand. All of this, it was just water here. So they artificially made all of this. So as you can see, there is no slope in this particular area. This is just an example that I could find of the internet. There is no slope. It's relatively flat. So in these type of instances, these guys, they actually use vacuum sewers, right? I also see mostly islands areas, they also use vacuum sewers because it's also flat terrains, and most of them probably they have got like unstable soil as well. So most of the sanitation that they can employ in that particular area, it's vacuum sewers, right? So this is just a case study that I came up with, right? So yeah, I'm not going to go much into detail on that one. I just wanted to share that with you guys. Should you need the notes, you can reach out to our captains. They should be able to provide the notes for you, right? So there are pros and cons to everything as well. So I'm just going to speed through that one. Now, this is the one that I also want to talk about because it's also mostly applicable to us in Africa. We've got a small bore sewers, right? I've actually done this one. That's why I'm also passionate about it and I wanted to share it with you guys. Now, small bore sewer systems or small diameter gravity sewer, or it's also called a solid free sewer, are also called septic tank influent gravity sewers. Excuse me, someone have their mic unmuted and it's distracting me. Vincent, can you please mute your mic? Vincent, if you can hear me, thank you, sir, thank you. Now, let's talk about this one, small bore sewers, right? Like I'm saying, I just like to call it a solid free sewer or a septic tank influent sewer. So, as you can see from the picture, it's pretty self-explanatory. As you saw from your conventional sewers, you've got your typical house, right? And you've got your typical house connection, then that gets into your sewer network. But in your small bore sewers, it first of all gets into a septic tank, right? Now, let me just quickly sketch a septic tank for you guys. I know most of you guys know what a septic tank is. So you're having a septic tank, it will be something like this. probably with an inlet there, right? Then probably a baffle there, then something like that probably. Then we're having maybe a pipe. Then we have got water that goes on the other side, right? This is just a sketch, it's not very accurate. Then we're going to have an outlet there. So particularly for this particular situation, we're going to have water that comes in here, like the wastewater from the house. So what then happens is that the solids will settle in the septic tank. So what only leaves the septic tank is only the water, right? That goes here, then from here it goes out. Then instead of going to what you call it, to a soakaway, it's probably attached to a sewer pipe. So instead of it going to a soakaway, it's attached to a sewer pipe. So this is a very interesting technology. I was actually happy to also implement it on some other project that we're working on. It was something that blew my mind, right? One of the ways that you can actually use this is maybe, let's say, in a situation where you want to save costs, right? Why? It's because most of your solids will settle into the septic tank. So only the water or the wastewater is probably going to be connected to what? To the pipe. And one thing that you also need to understand about a septic tank is that there is probably natural processes. So this water is partially treated. So by the time it gets to the pipe and then taken to the wastewater treatment facility, there is already a decreased BOD quantity in the water, right? In that wastewater. Like there's already partial treatment that has already occurred. Right, so this comes with its own advantages. I actually prefer this method in most of my sewer designs, not particularly in the urban areas. No, it won't work, but in the peri-urban areas, I always want to go for the small bore sewers because the reason why, the moment we have a small bore sewer, because like we're saying, all the solids are going to collect in the septic tank, only the effluent is going to be channeled into the pipe. Therefore, we don't really need bigger pipes because we're not going to worry about any solids collecting, right? So one thing that you need to understand that small bore systems, which is also solid-free sewer systems, right, is a system of effluent conveyance which uses an on-site tank to settle solids out of the sewage and conveys the liquid effluent only to a central treatment or a disposal point by means of sewer network. Just like what we discussed in the conventional system, where we're saying there's probably going to be a network of pipes. But now the difference is this one, the pipes are not transporting solids. The solids have already collected in your septic tank in your house or wherever you are, wherever you have your septic tank, right? So the on-site tank could be a septic tank, it could be an interceptor tank, or an aqua preview, or an anaerobic digester, like that you can choose. But mostly we usually go with a septic tank or an interceptor tank, right? So most of the suspended material is removed from the wastewater flow by this tank, reducing the risk of clogging to occur. The sludge remaining in the tank must be removed by means of vacuum tanker and transported to the treatment works, just like how you clean or you empty a septic tank using a honeysucker, right? Now, so the difference between a small bore system and a gravel system is the inclusion of a septic tank or an interceptor between the house and the main sewer distribution line, just as I was explaining. So the interceptor tank prevents gross solids from entering the main sewer. The connection pipe that conveys effluent from the house to the tank is typically 100 millimeters to 150 millimeters in diameter, right? Now, this is a very important point. I want you guys to pay attention. Unlike conventional gravity sewers, which are designed for open channel flow, small bore sewers may be installed with section depressed below the hydraulic grade line. That is, you have adverse slopes. Thus, the flow within the small bore sewer may alternate between open channel and pressure flow. The system pipes can therefore be laid at flat gradients as they do not carry solids that require transportation at scouring velocities. So these are some of the advantages to say, listen, I'm in a peri-urban neighborhood, and I'm in a relatively not so rich neighborhood, or maybe we've got a small budget to deal with sanitation in that area. We can literally go for a small bore sewer. because each house can then come with the condition. You say if you're building your house, then you have to build your own septic tank. And the septic tank is not that very difficult to build, just brickwork and a couple of cement and concrete, we are done. So if each house has got a septic tank or an interceptor tank, that could really help with the design of the sewer system, because in this particular sense, we don't have to worry too much about the slope, because we do not have suspended solids that have got the risk of settling in your pipes, because all the solids are going to settle in what, in your septic tank or in your interceptor tank. So the only thing that you have in the pipes is just the wastewater only, with no solids. So we can literally employ very flat slopes with this one, or we can even have alternating slopes where one part of your system is under pressure, the other one is just under flowing under gravity, or maybe one part of your pipe is flowing below the hydraulic grade line. It's very much acceptable. So this small bore sewers are actually just slowly becoming my favorite type of sewer to design. I have faced a couple of pushback, especially when you now introduce the concept of each house having to build a septic tank. Then usually you face a little bit of pushback. But if you can then explain the advantages of this system, especially in the peri-urban areas, it could work amazing wonders, because it's very cost effective compared to the conventional gravity sewers. Remember, we're saying the pipe is not carrying a lot of solids, probably less than 5% of the solids, right? So we really don't need steep slopes in this particular scenario. So we're going to have very shallow slopes, which then simply means that we're going to not have a lot of earthworks. Therefore, our project is going to be relatively less costly. So this is one of those technologies that I'm actually slowly liking in peri-urban areas, right? Not in high density areas. No, this is not going to work. In high density areas, you just have to go with the conventional gravity sewer lines. But in peri-urban areas, small bore sewers definitely work. And also, like I'm also saying, like the moment your sewer gets into the sewer pipeline, it's already partially treated. By the time it gets to the treatment plant, particularly for the reason why I'm also going for the peri-urban area is because usually in peri-urban areas, they are low income to middle income, but mostly low income housing schemes. So what we could do in this particular case, rather than having a biological nutrient removal treatment plant, we can just have stabilization ponds. So we can place, we don't even need to place an anaerobic point anymore. We can just have a facultative, or actually we can have not even have an integrated facultative and one maturation point. And then we can have a disposal of the water and it can be treated. Because by the time the water is flowing to the treatment plant, it's been partially treated already because of the septic tank or the interceptor tank that you've connected to your house before you connecting to the tank. So this is also a very interesting way of dealing with wastewater in a very cost-effective small bore sewers. These are my favorite as well. They're it's very advantageous anyway. So main design guidelines, we've got the hydraulic design, the design flow estimates. The sewer must be designed to carry an expected peak hour flow. There is less inflow and attenuation is created in these interceptor tanks, and thus the average daily wastewater flow per capita is approximately 190 liters per day. This is per dwelling unit, right? Now, the collector mains, we have got the layout. Small bore sewer distribution systems are often installed in front of the properties underneath the pavement. The alignment and grade, right? This is just the alignment and grade. The horizontal alignment does not need to be straight. That is, it can be installed to avoid obstacles. By obstacles, we mean it can go under the hydraulic grade line and also go up, right? Unlike your conventional gravity sewers where we need to maintain a steady slope going down, right? Here, if we've got an obstacle, we can have, this is where also maybe we can use what we call an inverted siphon, right? Just look it up, it's quite interesting. So with a small bore sewer system, we can use inverted siphons. We do have the license to do that, right? Remember, we don't have that much, less than 5%. We have very little solids in our systems. So we are good, we can get away with it. So the vertical alignment does not need to be uniform, provided right? The hydraulic grade line, you see, we spoke about this. It does not need to rise above the upstream of the interceptor tank or outlet inlet during peak flow conditions, right? Primarily because we don't have solids. So this is a huge advantage at our disposal. So service laterals, typical service laterals between tank and the sewer lines, 100 millimeters pipe diameter PVC. The connection is usually with a T fitting, right? So you would also realize that your serving lines, they don't have to be big, right? So you'd realize that maybe you would find that maybe your sewer line or your trunk line can be as big as 200 or 250 millimeter diameter. It doesn't have to go up to 400 or 500 because you've got no danger of having solids in your system at all, right? Because you're just purely carrying water or wastewater. So this is a huge plus in terms of cost if you're doing a cost-based analysis, right? Then you've got your interceptor tanks. I would prefer to just use septic tanks, right? So these ones should be located where they can be easily accessible for periodic removal of accumulated sludge, right? So obviously the guys that run the business of having honeysuckers, they're probably going to have a lot of money in this scenario. But I do favor the small bore systems. I'm quite passionate about it, provided the amount of pros that it has against the cons that it might have. So it can have a low flush. Low flush can be used since the solids only need to be conveyed over a short distance, right? So even, you see, you can also employ this in an area where there is not a lot of water. Let's say, that's why I'm emphasizing this whole peri-urban area, because sometimes in the peri-urban area, like in some of the communities that I work with, they've got intermittent water supply. They don't have 24/7 water supply like people who live in the urban areas like us. Like you wake up at 3, 24/7, there is water every day. In some communities that I work in, especially in the rural part of South Africa, we're having only 2-day water supply for the entire week. So think about it. So if I do a conventional sewer system for a neighborhood that receives water only 2 days a week, your system is going to fail. Just think about that. Your system will fail. Why? It's because we do not have enough water. So what then happens in that other 5 days when there is no peak flows? Because if there is no water, then there is no peak flows. Everybody is using water conservatively. So there's not enough flushes that are going into the system. So we don't have excess water to carry the solids or the sediments downstream. So what that happens is that during the 5 days, the sediments accumulate. Then maybe that 2 days is not enough to produce enough water to move the sediments downstream. So these are also some of those questions that you need to ask yourself. So if I'm to design a sewer system for an area like that with those conditions, I'm definitely going for the small bore system. It makes so much sense for me because I'm dealing with the solids right at the septic tank. Then even if we don't have water for that other 5 days, we know that the only thing that we're having in our system is wastewater only. We do not have any dangers of having solids, right? So that's just one of those other things. So simpler treatment process for settled sewage, like I'm saying, simpler in the sense that you can just do stabilization ponds for this one. There is really no need for us to invest in a BNR here. It's very expensive, by the way. So you can just do stabilization ponds, just have an integrated facultative, then have a maturation, then we are good. 2 should be sufficient. And we're not going to have an anaerobic because we are not having solids coming in anyway. Flatter slopes and velocities are acceptable. So flatter slopes and low velocities are acceptable. Elimination of costly manholes. These can be replaced with cheaper cleaners. So instead of having our precast manholes with staplings and everything, we can just have cheap cleaners, right? Low operation and maintenance cost. Water use can be limited, thus reducing operational cost, right? The only con that maybe can be a big deal, particularly the pushback that I've experienced when I was pitching some of these ideas, was the dislodging of the tank and the remove and the disposal required by the local municipality. So the argument, I remember actually making a presentation. The argument was, okay, fine, if each house is to have a sedimentation, a septic tank, right? Whose responsibility is going to be to empty the septic tank? That's where the argument was. That's where the argument was. Byron, please mute your mic. Byron, please mute your mic. Thank you. Right? Right. So that's the argument. So the argument was, who is going to fit the bill to discharge the septic tank? Is it the owner of the house or it's the local municipality? Right. So if you can try maybe in trade and talk to the municipality or talk to you do your stakeholder consultation and try and strike a happy medium and deal between those two, you could actually use a small bore sewer system. Right. There was a lot of pushback there because the locals would say, why should we have to pay for the dislodging of, of our septic tanks? If you guys are proposing these systems, then you should cater for some. Then the council would say, well, listen, we're going to have to make you pay for a sewer fee every month. So probably that was now like the agreed fee. It's okay, we're paying this amount of month every month. Then the municipality will be the one responsible for dislodging the septic tanks, right? So this is very important. So that's why I wouldn't go for interceptor tanks. I would just say let's go for septic tanks because it also it solves the treatment question as well. It partially treats the water because there's a lot of biological processes that are happening within the septic tank. By the time the water leaves into the system, going to the treatment plant, it's been partially treated, right? So it just saves a lot. So this is my favorite usually when I'm working with low cost housing in peri-urban areas. I always go for the small bore system, right? So listen, for the technical design standard, someone was asking me, so in South Africa, we've got there's this organization called the CSIR. It's the hub of mostly all the research that goes on in Africa. So they did a couple of researches. That's also the manuals that I read. They're quite good. Also, just knowing these guys, like especially when you're designing infrastructure like sanitation, there's a lot of stakeholder consultation that is required as well from your part, right? Because why do you also need to do stakeholder consultation is you have to understand the economic situation of the people that you're designing the system to, their culture also plays a role. Someone is unmuted, please mute your mic. Mr. Byron, please mute your mic. Thank you. Right. So I'm just hammering the point of saying stakeholder consultation is important because it helps you understand the economic behavior of the people that you want to deliver the project to. So you design your project, and it's not the most viable sanitation solution for that area, then it's not going to work. Like for this project that I was working at, these guys literally, when we're doing our stakeholder consultation, literally said we only receive water 3 times a week. So that then plays into the decisions that we have to make as engineers. Should we go for the conventional? This system will probably fail because it is going to be clogged. Okay, fine. If we're going for the conventional, then we're going to leave room for, we have to design our system in such a way that the council should be having the equipment to periodically clean the system and operate the system and maintain the system. Then that raises the O&M costs exponentially high. So stakeholder consultation is important for you just to understand the basic idea, the basics of how those people live. So it's quite important, right? Then the last but not the least, the shallow sewerage system. Now this is quite interesting. I've been to some very, very weird areas in my life, and this is also something that can be used. So shallow storage system, as you can see, like as you can see from this picture that I had to do a lot of research. This is the best I could find. You can see that you just have houses that are sort of like haphazardly connected with each other. Right, there is no set um, pattern of these houses, but they're just sort of like haphazardly placed there. You can use what we call a shallow sewage system, right? So a shallow sewage system, or it's a simplified sewage system, it's an offsite sanitation technology that removed wastewater from household environment. Conceptually, it is the same as the conventional sewage system, but I just want you to take note, conceptually, it is the same, but with conscious efforts made to eliminate unnecessary conservative design features to match the design standards of local circumstances. So one of the things that I can tell you is that this one is more of it's an unowned, okay, what's the term? Maybe in layman's terms, I can say that the conventional source system is like the official source system that we know. This is like the unofficial source system. You understand? Like for instance, there is already a housing scheme that is existing already, right? But we need a way to deal with sewage system, right? We can just have a shallow sewer system. Now, a shallow sewer system does not have the restrictive design parameters that are required when you're designing a conventional sewer system, right? And usually, this simplified sewage, it's usually employed by communities like low income communities, right? Um, so usually they can't afford the conventional sewer system. As you can see, it's just probably houses, and the pipes don't have to move in a straight line like how we do it in a conventional system. It's just haphazard, right? So many of conventional storage design standards, such as your minimum diameter, your minimum slopes, and your minimum depths, are relaxed in shallow sewer systems, and community-based construction and operation and maintenance allowed. So this is more of a community-based, right? So it's a simplified in the sense that it's coming out from a conventional system, but it's more simplified. It's more of, in quotes, in an official system, right? So you'd realize that the block feeder sewers are arranged in either three positions depicted in the fig. So as you can see, this usually is the backyard, right? Or mostly known as the mid-block section, right? Where you're saying, okay, this will probably be your road, this will be your road, and your sewer line will probably be sort of like threading the needle in between the houses. And as you can see, it's not straight like the examples that we've been seeing earlier before. It's just going in such a way that it's going where it can connect to the house, right? So it can go this way, it can turn, it can probably there's a house somewhere here and there's a house somewhere here, right? So the minimum diameter of the block feeder pipes is usually 100 millimeters. The block feeder systems are different from conventional street sewers, mainly in three ways. The pipe diameter, 100 millimeters versus 150. The gradients, 167 compared to 1:60. Then the inspection chambers are used instead of manuals. So this is a very simplified. So imagine taking a conventional sewer system, then using it in a simple way. So the applications, somebody might be asking themselves, okay, fine, Baron, what are the applications? The applications maybe we're saying in an area like this, like it's a low cost housing scheme. Like there's already people that are already living there, but we need a way to deal with sanitation there. We can just have a very shallow sewer system in that particular area so that we can just remove water from that area, the wastewater, then probably have maybe your stabilization ponds this side so that you can partially treat it before you can dispose it into the river. Because like, think about it, in an area like this is probably a bigger population for each house, or is it okay? It's more densely populated for each house to have their own individual toilet or their pillar tree, but it's also too big for them to have one common toilet or a bathroom. It is very unhygienic as well because people have got different hygiene habits. So in a situation like that, we would probably need a shallow sewage system where you're saying, okay, we're having a feeder there, then it turns there. It's very haphazard and it's very unofficial like in layman's terms, if I'm explaining it, right? So this is what you usually use probably in squatter camps, right? Those are like low income housings, right? Because in as much as some of these houses will, because you'd realize that in some countries you do have problems with squatters or unofficial housing where people just invade a space and they just start erecting structures that are unofficial. In some instances, you can't evict them because of human rights, and it just gets very political very fast and just so in a situation like that, what do? You might need to use a shallow sewage system there so that you can just take out your wastewater in that particular situation. So this one, it's quite cheap. It doesn't really take a lot of money. It doesn't cost that much, right? The main design guidelines, the minimum cleansing velocity in shallow was 0.5, right? It's different from the one that we had proposed in the conventional one, right? The pressure force of the water backing up behind the solid in smaller pipe flushes the solid down the system, and this is the main reason for the relaxation of the minimum self-cleansing velocities. Based on the acceptable practice, a minimum flow depth of 20% of the pipe diameter and a maximum flow depth of 80% of the pipe diameter is suggested. Shallow sewers use 100 mm piping where possible, only increasing when estimated peak sewage detects, right? So yeah, guys, those are basically the four. They are not the only sewage type solutions that are out there, but the ones that I really wanted you guys to just know, these are the four that are slowly being used, that are commonly being used in our urban areas. So these are more of your off-site sanitation source systems. Maybe in the future, not maybe in the future, we're probably going to be talking about your on-site, then also talking about your wastewater treatment plant. How do you deal with the waste now that you've taken it up? So let me just check the chat box real quick. I'm over by 1 minute. Allow me to just take like 5 minutes of your time. Then I can see what to do. I would just start with Shadrach. How can we get the catchment area for the actual location? Can I have more context on that one, Ahmed? Can you mention sample? I've already answered that. How can we get the catchment area for the actual location? I'm not so sure how to answer that and what the
Yeah.
context is.
What is that?
Yes, you can go
Yeah.
ahead.
The reason why I asked about the catchment area is because in hydraulics, discharge is equals to area times velocity, depending on the dimensional analysis that comes along the way.
Mhm.
So now,
Mhm.
if we are doing about we are working about, we are dealing, the project now is about sewer. So before we
Mhm.
can say, okay, this is the size or the diameter of the pipe,
Mhm.
so there must be a discharge. And when there is a discharge, there must be an area. So are we getting the
Okay.
area first before we get the discharge?
Mhm.
Or how are we going to put in the parameters into consideration?
Okay, I think I understand your question. It's a very good question. So, um, how can I answer this? Okay, let me start by saying this. Whenever we're talking about the catchment area, we usually use these terms when we're doing our stormwater analysis, where we're saying discharge is equals to Q is equals to CIA, right? Where you're having C, the coefficient of flow, then I, your inflow, then your A, which is the catchment area. So in sewers, right, if you're calculating your capacity, right, there are two methods that you can use. You can use what we call the equivalent population method, right? So the equivalent population method, this is where you're using the catchment area, where you're saying, okay, this is the area that I have, and particularly in this area, according to the codes that we have in this country, this area produces this amount of discharge, right? So it's called the equivalent population method, right? So there is like a whole formula in how you actually calculate that in depth that I cannot do now. But what I was discussing when I was talking about the conventional one is we just literally use the demand of each house and the return flow. So instead of, I don't usually advise people to calculate the catchment area right? Because in some countries we don't have accurate data for that one. But what we do have accurate data, it's the demand of each house. That's why I was asking you to say, how much water do you think you can use in your house? Then if you have an approximation of how much water you can use, then you can have a return flow factor to say, okay, fine, from this water, if I'm getting 100 liters of water a day, approximately I'm probably going to use about 25% to do what I do. Then the 75% can go back into the sewer system as what is sewage. Because some people would take some of that water their flowers. It's impossible to have all the water that come into your house and go back into the sewer system again. Some people would take that water their flowers, do some gardening and everything. So that's why you have a return flow factor. So I genuinely discourage using the catchment area method. That's why I like using the demand method to say, first of all, calculate the demand that's coming in your house, then have the return flow factor. Then you know that each house is contributing 85 liters of sewage. Then how much houses do you have? If I've got 10 houses, I know that I've got 850 liters of sewage that are coming per day. Then you employ your peak factors. You add your peak factors there. If it's 2.5 or 3, depending on the population, then you factor in your stormwater infiltration. Then you now have your design flow. That's the one that you use for your capacity. This is just me chopping it up very fast. Of course, there's a lot of things that you need to add in there. So yeah, I don't usually encourage people to calculate the catchment area, but should you need to know that, you can maybe reach out, then maybe we can have a conversation with that. But there is a method that you can use called the equivalent population method. Now, someone is saying, how is the small bore system advantageous as a sanitary sewer? Like I've already mentioned, Shadrach, it's low cost, number one. Number two, we can use small diameter pipes, right? Because we don't have suspended solids in it. Number three, we don't have to trench very deep. We don't have to worry about slope per se, because number one, we don't have suspended solids in the system, right? So our pipes can go below the hydraulic grade line. It will still be okay because it's just wastewater. And maybe number four, we can say by the time the water reaches the treatment plant, it's already been partially treated in the septic tank. So there is no rigorous treatment that will be needed to be done at the treatment plant anyway, right? I'm not saying there's no treatment at all, but I'm saying it has been partially treated. So our treatment method may be relaxed. We might not need to have a full BNR system that is very, very costly. We can have stabilization ports for that one. So that's how I would take that. Lesho says, imagine for a household, there is an added burden to manage the settled solids in the septic tank. The municipalities generally don't do well in servicing septic tank. Kindly comment on how this has been handled in your experience. Right, this is how they handled it, because the pushback, right, when I presented the solution and the advantages, the pushback was, yes, who's going to fit the cost of the honeysucker to empty the septic tank? But eventually, as you guys know, that whenever you pay your bills to the municipality, there's what we call a sewage bill. So they eventually agreed on a sewage bill. It was slightly higher, but they eventually agreed on a sewage bill to say, listen, we are going to pay an extra sewage bill. Now, with this sewage bill, the council is now obligated to have their own honeysucker that will be emptying the septic tanks periodically. So that was the agreement. So whether they follow through or not, I'm not sure. But if they actually follow through, I think it would be a very good solution for everyone. So it was just politics. It was just politics. How about having septic tanks on the sewer lines after connections from the number of households? Okay, sorry. How about having the septic tanks on the sewer lines after collection from a number of households, and have like an in-between conventional sewer and a small bore? So maybe you are saying a hybrid of the two. Yeah, that's a good one. I've actually never given it a practical thought, Michael. I think that could work. That could work. I'll be curious though, like how would you do your configuration? Like, are we saying instead of each house having their own individual septic tank, maybe we say 10 houses, they've got like one communal septic tank, then connect from there going forward? So maybe having like a hybrid of the two. Yeah, I've never thought about that, but that's actually it's an interesting idea. I'll look into it. But thank you for bringing that up. I've never thought about that, right? Leslie again was commenting, will the main course training include the pump station as part of the sewer reticulation system, the wastewater treatment plants, right? The main course won't be including the pump station. The pump station it's quite an in-depth analysis on that. But we should be doing that sometime in the future, right? But should you have questions regarding that, you feel free to reach out. The team will help you. How feasible and sustainable is a separate source system compared to a combined source system? That's a very good question, Daniel. Like, I usually favor a separate source system compared to a combined source system, depending on where you are. So I live in South Africa, so yeah, we are not a desert at all compared to other countries, in the sense that we do receive a considerable amount of rainfall. So with that, there is unpredictability that happens. We can't predict for sure how much rainfall we can receive. Like for instance, it rained a few days ago and we're supposed to be in winter. It's things like that. So imagine if you have a combined sewer system. If you have a combined sewer system, which means all your pipes have to be larger because you are catering for your sewer system and you're also catering for your storm sewer system, that's just storm water that's coming from the rainfall. So your pipes have to be larger so that you can cater for those two, right? But now the challenge for that is how then do you size your wastewater treatment plant or your wastewater infrastructure? That's where the challenge is, because sometimes you can then size your clarifiers, your aeration banks, and all these other things. Then you receive more wastewater than you expected. So the challenge might be that we might discharge effluent into the environment that is partially treated, which might be a problem to the environment. So yeah, the combined source systems are a bit tricky because it's very difficult to accurately size your wastewater infrastructure, because sometimes you can't accurately predict how much wastewater you can receive, due to the fluctuations of rainfall. I know in some areas, of course, they've got the main data, so they can predict how much rainfall they have. But yeah, in terms of having to accurately then size your wastewater treatment plant, in my experience, that has really proven difficult, because when you have got a combined system, then let's say you have designed your BNR to receive like 3 megaliters a day, then you have got floods that you did not anticipate, right? Then instead of receiving 3 megaliters a day of wastewater, you receive 5 megaliters or 6 megaliters. Then that's a problem on your wastewater treatment plant. It simply means that most of the water is going to be released into the society or into the community or into the rivers partially treated. Then that's a problem. So feasibility, I would say it depends. In very arid places, like in very, very arid places, maybe you can do the homework on that, like maybe in areas where they receive zero to no rainfall at all, I would say you can go combined sewer systems, because you know that they might not have rainfall, but you might need to be careful as well, because there's global warming or global climate change. I don't know. But in very arid places, I would mind having a combined sewer system so that we don't have two separate pipes, because it's expensive to lay storm water in sewer. But in any other areas, like the areas of Nairobi and all these other areas, Kenya, it's quite humid, it rains a lot. The combined source system won't work. I genuinely discourage that. I would go for a separate system. So yeah, that's my answer there. That's my answer. So I prefer a separate because of where I am, but a combined does have got its own perks as well, depending on where you are, right? So yeah, I think those are the only questions that I have. Yes, those are the only
Engineer.
questions that I have. Yes,
Hello,
yes,
engineer.
I'm going to take you the last one because we're over by 13 minutes. Yes, you can ask.
How are you, Engineer Bill?
I'm very well said, thank you.
Maybe mine is just to table an observation
Yes.
about the septic tanks. So I think the septic tanks are prone to leakages.
The septic tanks are what? Sorry, come again?
I'm saying
Yes.
the septic tanks are prone to leakages.
Okay, okay.
Some years back, I was engaged in research about the underground water,
Mm-hmm.
and I sampled an urban area in Kenya named Juja.
Mm-hmm.
In this area, I sampled 5 boreholes, that is the shallow wells,
Yes.
and I came to find that there was contamination of the E. coli for the
Yeah.
boreholes,
Yeah.
and that means that there were several leakages for the septic tanks.
Mm-hmm.
So I don't know what you can comment as an engineer about the functionality of the septic tanks because of the leakages. I think they contaminate the groundwater. So I don't know what's your view about that.
Okay.
And also I have a question about the cost benefit analysis. For the case of a water service provider,
Mm-hmm.
after how many years can we release that the sewer is generating some income? Now comparing the cost of maintaining the sewer system and the cost of and the income generated from the same sewer system.
Okay.
Yeah, so I have those two views. Maybe you can comment on the first one about the leakages of the septic tanks and how they contaminate the groundwater, and also the cost benefit analysis of the income of the same sewer. Thank you.
All right. Thank you so much. No, those are very, very, very good questions. Maybe I'll touch on the septic tanks and the leakages. We actually had an incident where there was a septic tank that was not properly done. And I think in this particular case, soil tests were not properly done at all. And then, yeah, the soakaway was not functioning very well, and the whole thing was clogged. So it was a serious issue in terms of sanitation. So I'd say, yeah, there are. I have encountered situations where we have bought septic tanks that were not properly done, but the assumption is it's the best solution in this case, depending on what you have on the ground. So if I'm going for a peri-urban area, yes, I do have the allowance that there could be a leakage in the septic tank, but it depends on the construction. I think all boils down to the construction, right? It has to be done properly and it has to be done up to the standard, right? In the situations that I've been in, I haven't really encountered a septic tank that has failed to that level, right? And also, it's probably each house it has a septic tank, right? And I think even if there is a leakage, worst case scenario, it's not that bad, right? I'm not advocating to say any leakage is any good. I mean, best case scenarios, we don't need any leakage at all. So I would say, yeah, it's a very legit concern, but I would say as well, if this system functions the way it has been designed to function, I think it actually functions properly and it functions well. So that would be my take on that. That's how I would comment on that, right? Then the second one, the cost-based analysis. Uh, I've actually never, we've actually never implemented it. It's something that we actually just discussed to say, okay, fine, is there a way that we can realize some revenue from the sewage, from the sewage collection systems? And one of the ways was probably because there's this urban area that we were trying to develop. So instead, there was no municipality connection lines in the area. So the obvious case was for us to have stabilization ponds. Then from that stabilization ponds, then that water can be used for irrigation. So that was the easiest solution that we could come up with. But in terms of realizing revenue from sewage, I've never done that per se, like to actually do a cost-based analysis in detail. Something that I've just had a conversation with people here and there, but I've actually never done it. So I'll be very curious if you've done it before and you've got some knowledge, would you please share with? I would appreciate that. So thank you so much for asking those questions. Guys, thank you so much for attending our webinar. I would really appreciate you. Thank you so much for supporting us. I realize that a lot of people have left. but it's still fine. I realize that there are also some questions. You know, we are roads up. I'm here. We are not going anywhere. Thank you so much for attending. So the question is, what now? You can take action. We do have an upcoming course, the sanitary sewer, that is probably going to be starting next week. So we still have a couple of slots open. They're filling up faster than I expected. So please make sure that you take and fill up a slot. In the course, we'll probably be having, as you all know, if you've attended any Roads Up course, we have got what we call feedback sessions. This is where we probably get to discuss some of the questions that are being asked here in detail, or be it a sump design, pump station design, under what conditions, you know, all these deep questions. So we do have an opportunity where we can actually chat and actually discuss more of these things in detail. So yeah, we do have an upcoming course coming up next week on the 10th of June. So do sign up. We do have a couple of days left and the slots are filling up. So thank you so much, guys, for attending. We really appreciate you. Should you need the recording, follow Roads Up at all pages. We are there on LinkedIn, on Facebook. We are probably there on YouTube. All our material is there on YouTube. So subscribe, like, share, comment, but everything is going to be available for you guys. So thank you so much. God bless. Have a good night. Cheers.
Thank you. Thank you very much, engineers, for attending this webinar. We hope that it has been informative for you, and I hope that you have gathered one or two points. Please remember that we will be having an official training that is starting next week on Monday, that is on 16. It is entirely centered on sanitary sewer design. I am going to send in a link here, should you probably be interested to join the program. It's going to be very extensive. And we would, of course, love to have all of you join the program. We have the capacity to attend to each and every one of you. Program is $75, just like engineers said. And I believe that it's something that has served many engineers, and we believe that it's going to serve you as well. So please, if you think this is a program that you would want to enroll into, I've sent the link in the chat box. You can be able to buy directly from the website, and you'll be able to get in touch with you. Engineer Baron, thank you very much for leading such an informative session. We thank you for sharing your knowledge with us. We really appreciate way beyond the allocated time. So thank you very much. May we all have a fantastic night. Please, in the next webinars,